In Chapter 7 here, we're going to talk about something called the central limit theorem. So the main idea of the central limit theorem is that if we collect a large number of samples here of the same size, and then find the means of those samples, and form a histogram from the sample means, then that histogram is going to be approximately bell-shaped if n is large enough. So if the sample size is large enough. So let's illustrate the central limit theorem here by doing simulation. So take this URL here and paste it into your browser and go to that site. If you do, you shall see this. So this will pop up, this website. You're going to click Begin. And then what we're going to do is we're going to look at repeated samples of different sizes. So we'll look at samples of size 2, then size 10, and then size 25. So those are the values of n. So we're going to select a normal parent population and then draw 1,000 samples of each size and then look at the shape of the distribution. So here's our parent population. We can choose normal, uniform, skewed, or custom. We're choosing normal. Our sample size is down here, n equals. So we're going to do samples of size 2. And then if you click the animated button, there's our first sample of size 2, and then the mean of those two numbers right here. And you can see it's right in the middle of those. Click animated again. It picks another sample of size 2, and then the mean, go down right in the middle, right there. And so if we keep doing this, it picks repeated samples of size 2, one sample at a time. And then it forms the histogram. You can see where the means pile up down here. So if we do 5 samples of size 2, click the 5 button. So it doesn't animate it, but these are the 5 means. And then we click again and again, and we keep going. So we're adding 5 means of samples. So it picks 5 samples and finds their means, and then it's adding them to the histogram. So we want to do 1,000 or 10,000 of those samples. So if we click the 10,000 button, now I can see this is 10,000 samples of size 2, and we can see this distribution. Although it started out, we couldn't tell what it was going to be, but now it's looking like it's approximately normal. We can pick 10,000 again and again and again. You can see it's even getting more and more bell-shaped. So what we are seeing here for samples of size 2, the distribution shape in there is normal. Let's look at samples of size 10. So now we're going to click n equals, well, let's go ahead and clear, press the clear button, and then switch to n equal 10. And now let's do 5 here. So, well, we'll do one animated first. So there's our 10 values in our sample, and then the mean of those 10 numbers. So now we do 5 samples of size 10. You can see them pile up here. It's starting to look bell-shaped. So if we do 10,000 samples of size 10, there we go. Or 100,000, there. So we can see it's getting bell-shaped, but it's narrower. But it's still normal, still bell-shaped. So this one here is also normal. And then we'll do the same thing with samples of size 25. So now we'll clear this out. Look at samples of size 25. So we can do 5 samples of size 25. So those are the 5 means. Keep going. And we do 10,000 samples. And we're seeing again normal. But it's even narrower. So it's got a smaller standard deviation. So we can see that in all cases, as you take more and more samples of size 25, those are normal for size 25 repeated samples. But for all sample sizes, if you start with a normal distribution here, your distribution of means of samples is normal in all cases. So I want you to repeat this process for a uniform parent distribution and then a skewed parent distribution for samples of size 2, 10, and 25 for the uniform, 2, 10, and 25 for the skewed. So you're going to come back here and you're going to clear this out. You're going to change to a uniform distribution. So now our parent distribution is not a normal distribution. And you're going to go ahead and pick repeated samples here. So you can just do the 10,000 if you want to. And then do the same thing again with a skewed, starting with a skewed distribution, and see what you get. So pause the video now and try those. Okay, so if you did that, you should get, let's go back to our uniform. For our uniform, we've got samples of size 2. So if we do 10,000 samples there, 10,000 more. So it's looking bell-shaped. Well, no, actually, this one's not bell-shaped. It doesn't have the curves in here. It's not quite bell-shaped. So samples of size 2. This is looking like a what they call a tent distribution. So that's not quite bell-shaped. What if we do samples of size 10? So there you should get something that's normal, bell-shaped. And then samples of size 25, again, we get bell-shaped. So we go back here. There should be a tent distribution. But then these guys are normal. And then what if you start with a skewed distribution? Samples of size 2, 10, and 25. So parent distribution is skewed. If you take samples of size 2, do a whole bunch of samples, not bell-shaped. This is skewed to the right. What if you do samples of size 10? A whole bunch of samples. The distribution of means now looks bell-shaped. And then samples of size 25, do a whole bunch of samples, and the histogram looks bell-shaped. So the first one was skewed, but the others looked like they were approximately normal. So what we can see is that if you start with a parent distribution that is normal here, then the distribution of repeated samples of all sizes is normal. If you start with something that's not normal though, uniform or skewed, then your smaller samples are less normal. So you've got a tent distribution here, and this one was still skewed. It wasn't until we had larger repeated samples of a larger size that the histogram got more normal. So for a given distribution here, what do we notice about the shape of the histogram as n increases? Well, it gets more normal or more bell-shaped. So more normal. So what we'd like to happen is no matter what distribution you start with, we'd like to have this be normal, a normal distribution if our sample size is big enough. So we saw bigger samples, repeated samples of a bigger size were better. Well, how big is going to be big enough all the time, no matter what distribution you start with, normal, uniform, skewed, or something weird. So, and that's the idea of the central limit theorem. It tells you how big the samples have to be, repeated samples. So the distributions that we form, these distributions here, those are called sampling distributions of the sample mean. And we'll abbreviate that as SDSM. So if you see that abbreviation, it means sampling distributions of the sample mean. Take repeated samples of the same size, look at the distribution of the means of those samples.